Hello, this is Team N6 Wind Turbine final presentation by Eddie Mueller, Stephen Holland, Dason Tom, and me, Tristan Corniker. Some personal info about me. I'm a freshman studying mechanical engineering. My main contributions to the project: I work on the windmill, help build the MATLAB code, and fill out design journals. Hobbies: I like to go riding with buddies and go to the gym. And fun facts: I ride motorcycles. So, everyone's part: Eddie, he was the electrical management in charge of the Arduino and MATLAB measurements. Steven was the software engineer in charge of the coding and MATLAB scripts. Dason was the writer. He collaborated with the team and helped create the design journals and website summaries. And me, I was the researcher in charge of research about formulas, materials, and sources to help us complete our projects with accurate information. Summary of the wind turbine. During CEC 112, we created a wind turbine out of set parts. We spent many weeks tweaking and changing parts of our design to optimize the power output into a generator to read through our computer. Using a box fan, we created artificial wind to power the turbine, which let us finely tune our design to its best. In this presentation, we will go over our findings and display our final results. Some key theoretical concepts: materials, distance from the fan, generator type, angle, gear ratios, power, and efficiency. Materials. The materials we used included the plastic frame, metal axle, separators for the axle, generator frame, turbine blades, which included both wood and cardboard, and electrical components.
So these are the electrical materials that we used for the wind turbine. We have the electrical board, which is the whiteboard as shown in this image. This basically allowed us to resist the current and the input going into the Arduino. We have our alligator clips, which connects from the whiteboard to the generator, as well as the USB cables and adapters that went into connecting the Arduino to the computer to read the power output. We also have the Arduino board, which facilitated all of the coding and all of the output reading that went into the computer, as well as the jumper cables, which connected the Arduino to the ground and so forth. The distance from the fan was always kept at 1 meter, which helped us get a stable and consistent result. This also allowed us to measure the change when we tuned our turbine. This variable was kept the same just so we can get stable results and not have any varying results due to the distance. We also kept our angle at 70 degrees. We found out that this was the best for our wind turbine. This gave us the fastest speed out of all the other angles, which allowed us to get the highest power output. This is our gear ratio to power output table. We tested 2-to-1, 4-to-1, and 8-to-1, and found that the largest gear ratio, 8-to-1, was the one with the most power output at 0.1185 watts. We also developed the relationship between the gear ratio, which affected the speed of the input into the generator and directly influenced the power output. We also have our power generation for two kinds of materials of our propellers. We tested balsa wood and cardboard to calculate which one provided the best power input. As you can see, the cardboard had better readings, but we stuck with the wood due to its high durability. We We could have also bent the cardboard in a more effective way, but um, we didn't have the time to correctly like optimize our cardboard bending. So this also influenced our pick to pick balsa wood. Um, if we had more time, we would have definitely tried to optimize the cardboard bending a little bit more. And these are the graphs that we found in MATLAB, which shows our readings.
On the right is our table of experimental power, which we tested, and our table for maximum theoretical power, which we calculated using physics formulas on the experimental power tests. We did each experiment 3 times per fan speed, and our findings led us to efficiency average of 0.94. It's not the best efficiency, but um, given given our current scale, I think that when scaled up, it could be more efficient. And with slight alterations at the greater size, it could probably be driven even higher. In our final design, the most important experiments were the turbine blade designs, the gear ratios, and the efficiency experiments. These experiments allowed us to fully target certain aspects of our design and maximize the optimization of the speed and power. First, for our turbine blades, we tested the angle, material, and amount of blades we could use. And after testing multiple iterations, we found that 70 degrees with 3 wooden blades was our best option. Additionally, the 8-to-1 gear ratio gave us the best power output as it was basically the furthest we could push the input gear in terms of um, size and speed. And the testing of efficiency consisted of calculating our maximum power of our turbine, and that just allowed us to know what was being consistent and efficient. In between all 3 of those, they sort of form the backbone of how we were able to improve and maintain and document our design well. For the real world applications of our turbine, the most basic one, the most common one, is just electricity generation. That when someone has a need for electricity, that this will be one of the ways that they can get their electricity from. Um, it can also be hybrid with other power systems, such as solar or hydropower, and that will just increase the quantity of energy being generated in totality because the wind turbines require space. It's not entirely practical to solely work off of wind power, and so it's really best when paired with other things. You can use it to pump water in rural areas for irrigation or livestock. And then our last usage here is to bring electricity to rural areas. And basically, in developing countries where a grid may not be sustainable or practical, you can build wind turbines and utilize the natural geography of the area. And it takes up a lot less space than a full grid implementation. And it requires a lot less money and material, but can still generate electricity and bring it to these other areas where our kind of infrastructure is unsustainable. We chose the final design due to the fact that it produces the most electrical output, and we optimized our turbine blades angle and gear ratio to provide the most efficiency of electrical output. You can see in the video that it's spinning around with our optimized angle and gear ratio, and this is how we were able to find our most efficient electricity.
Okay. So these are the pictures of our final design. Um, we have this one right here. It shows our full wind turbine. It shows all the pieces, all the blades. It shows the gears, the wires connected to the computer. These two over here in the middle, they show the Arduino connected to the whiteboard with the alligator clips, connected to the generator for the electrical output. And then this one over here shows very similar thing as the first one. It's mainly emphasizing just showing the blades and how we have them angled and connected for our final design. Okay, so possible changes to the design. To better our design, we could reassess our points of effectiveness to find if we should change the angle of the blades to get a better conversion rate. The material could also be further researched to find if there is one that we potentially overlooked that would allow us to operate with less cost. The two biggest things here, for me at least, is the possible changes for a full scale design should look more into the longevity of the material that we're using. So like if a material is cost effective and it lasts longer. Um, but other than that, the angle of the blades too, super duper important. Um, because through our testing, we saw that certain angles work better than others, and produced more power. So other than that, we could have done further research into or further testing into which blade action or which exact angle worked best, but overall pretty good. Final conclusions. As seen in the power and efficiency slides, we generated little amounts of power, and due to this, we have a very low efficiency compared to full-size wind turbines. This is mostly due to the scale of our wind turbine and its efficiency being capped by the terminal speed of the blades. Industry wind turbines have a higher maximum speed and therefore more energy produced. Of course, ours is just a smaller scale version, meant to teach us how they really work. Of course, out in the field, they will be way bigger, produce much more power. Um, and all in all, our wind turbine was just a great way to see it in a smaller scale that we can actually put our hands on. Reflection, what we would change next time. Next time, we would likely experiment more with the curvature angle of the cardboard blades to optimize the airflow, which it would increase the speed of the wind turbine and efficiency. Other design criteria that we would have considered, of course, if we had more time, is we would likely want to optimize the power lines going into the Arduino, as this could be a factor to take into account when calculating efficiency. All in all, for us, we just had a severe lack of time. We could have done much more testing, but we were held back. I think we could say that for all of our work. We could have gotten more accurate and overall better results if we just spent more time testing. If instead of doing 3 trials, we did 6, um, something like that. Um, of course, the curvature angle, the direction that it's all in, for sure would increase our efficiency. But yeah, all in all, everything could have been increased. It's just lack of time. But what are you gonna do? Thank you.